Okay, so number 6. Yeah, number 7 has a little typo. Please don't move on to number 7 yet. Like it has just a typo in that there's an omission of a centering point. So we need to do something with that. But number 6 says find the first 4 non-zero terms of the general term for the Maclaurin. And when you see Maclaurin, then we know for sure the centering point is automatically 0. What was the easiest thing about number 6? Yeah, the derivatives, doesn't matter what degree it is, it's all just going to be e to the x. So that actually is pretty nice. So I'm going to say Maclaurin means c equals 0 for my centering point. Then as far as those derivatives go, I know that basically the nth derivative of x is just, or of f of x is going to be e to the x, right? It doesn't matter what degree I'm at. The answer will just be e to the x for those. So my first term is going to be f of 0. And what's f of 0?
1.
That's right. So I'll put my my Maclaurin polynomial is going to equal 1 plus. Okay, now the next term is going to be f prime of 0 times x. And so what's that?
X.
Just x. So remember from yesterday, if I stopped right there, what's that?
It's the tangent line.
That's the equation of the tangent line, right? So I could stop right there, but it does want the first 4 non-zero terms. So then the next term, it would be f double prime of 0, which once again is 1. So this would be 1x squared over 2 factorial. And then lastly, for the fourth term here, it would be f triple prime of 0, which again is 1. So there'd be 1x cubed over 3 factorial. And it's at this point that I have the first 4 non-zero terms, so I'm done with that part. Would you guys be okay with something like this? Right? That's not any different. This might help us to see the pattern. Perhaps we could even do something with that 1 at the start, because it does ask us for the general term. So I'll put plus ... plus the general term for this polynomial. I think the easiest way to write this would just be x to the n over n factorial, right? As n goes from 0 to 1. I'm starting at 0 technically here, so it would be from 0 to 1 to 2 to 3 to 4 to 5. Then I would get the exact same pattern using that nth term. And eventually we could write a sigma for this and get a full power series. And that's kind of what we're building up to. Okay, so in the midst there, I heard Peyton say, I'm just going to wait to see what he does with this. Are there any questions from anybody? Anything at all? Okay. So let's do this. Let me, just for the sake of a little more practice here, just to see how you all do. What if it was the exact same question, but instead of a Maclaurin polynomial, what if it was a Taylor polynomial at, I don't know, c equals 1. So what if I move the centering point from 0, which it was for our original exercise with this, maybe it could be c equals 1. Let's think about what that would look like. Once again, I'll give you a chance to kind of try that on your own. See how it all goes. So we did one like this last time where the centering point was not 0. This is another chance to practice that. Okay, so it's just Logan and Meg, right? I know about Meg and know about Logan. There we go.
Is that everything?
I don't know. Don't worry about the general term. No, I think that's good. So. So the nice pattern with the derivatives, of course, continues on even here with a different centering point. Makes it a little bit easier.
No. I've never fully tested my levels.
Okay, so I'll put t of x here for Taylor polynomial. You could put p if you want, p of x. What was your first term? Was it the same or different?
E. It was.
It's e to the first, right?
I don't know why I said.
It's got to be f of 1. So remember the way that we built this yesterday is that this first term, this constant term, has to be an exact match for the y value of the curve at the centering point. And so that's why this one's different, right? Because when c is 0 or when c is c is 1, you're going to get a different y value at that particular centering point. Okay, so then plus this first coefficient would be f prime of 1. So what's f prime of 1? E. In fact, isn't f double prime of 1 e? F triple prime of 1 is e
You betcha.
on down the list. So it's going to be e times x minus 1 to the first over 1 factorial. The next one would be e times x minus 1 squared over 2 factorial. And hopefully you're getting the idea here that this will just continue on in a pretty nice, easily discernible pattern. So Jack said something about the nth term. Did anybody try the nth term here?
Yeah.
I don't know. What could it be? It could be something like plus dot 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 plus e times x minus 1 to the n over n factorial. Something like that. Sometimes that nth term can be hard to decipher. One thing I want you guys to note here with these nth terms, all you're doing is looking for a pattern. So this can be one of those cases where it's possible that there's 8 of you, and we could have 8 different nth terms, and they could all be correct based on starting at different first values, right? So like if Aiden decided to start at n equals 0, it's going to look like that probably, right? If Santi decided to start at 1, n equals 1, then it would look a little bit different, right? So it's conceivable we could have some different looks, but they should still match the pattern as long as we start at the right numerical value. Okay. No comments that Aiden's right and Santi's wrong? No? Okay. They never let you off the hook, especially when you're not here.
Oh, yeah. it's probably
When you're
worth
not here. Yeah.
It is.
Okay.
No, it's pretty easy to talk
So
about them to your face.
this one right here, number 7. Number 7, I'm super excited to see what you do with this. Like I said, there is a typo by omission. This should say find the first 4 non-zero terms and the general term for the Taylor polynomial at x equals 0. I could have just written Maclaurin polynomial, of course. But I do want you to try this. This will take you a little bit more effort, maybe a little bit longer than the one we just did, like the e to the x. But it's totally worth it. And there are some analysis questions off to the side there. So once you think you have it, there's a very distinguishable pattern to this. And then we'll check out those analysis questions. So, like I said, give it a shot. See what you can do. And please, for goodness sake, don't use the quotient rule ever on this one. Just
Is that correct?
flip up. Just 1 minus x to the negative 1. That's correct.
Wow, Jack.
And you took a quick glance at it. It looked pretty good.
Just did it.
Wait a minute. Mr. Anderson. Oh, wait, no. I'm stupid. Never mind. Disregard.
Looks pretty good. You can start thinking about those questions.
Couldn't it be negative 1 though?
Couldn't what be negative 1?
Wouldn't this series converge if x equal negative 1? Why would it?
Well,
These
yeah,
don't cancel
I
each other
think,
out.
honestly, I think you kind of have to answer the first question before you can answer the second question. So what we're going to do, possibly tomorrow. Well, I don't know. We'll see if it happens tomorrow or not. But what we'll find out is that we can take that nth term that you just developed there, and we can use that to help us determine that interval of convergence that you see right So that definitely is the interval of convergence where, and when I say interval of convergence, I'm talking about where this is the same as that. If you move outside that interval, then those two things are not equal at all. But as long as you're within that interval, they are. So, but yeah, first question would help a lot.
Yeah.
As far as looking at the second
Minus
question.
1 plus 1 minus 1. Yeah.
Don't forget there's a chain rule in all your derivatives, and so every time you do a derivative, you should be multiplying by -1, right? Because the inside is 1 minus x.
Oh.
So every single time you're going to be
Wasn't
doing
doing that.
times -1.
Okay, Nick. Never mind.
Mr. Anderson!
Peyton!
Is it just,
Ah!
Oh, goodness.
Oh,
would it
wow.
just simplify it?
I would run if I were you.
Say it one more time.
Would it just simplify that you to the end every time?
Do that.
For x is
They'll
what
always
x,
cancel
x,
each other out.
x is what.
Oh, okay, yeah.
It's all
Yeah, x to the
positive.
end.
Yeah, so like your
Derivatives are all
Yeah.
positive.
It'd be x to the end.
And then think about what you can do even within your terms, right?
I mean, it would
Two over
simply
two,
cancel.
cancel,
Yeah.
sorry, Nick. 6 over 6, cancels, and so, yeah, bam.
So then it's
Exactly right.
Well, that's what we were doing too. Like, we got that.
You got the same thing as Sashi?
Yeah, well, we were doing that, it would come, like, the cosine would be 1 every time.
So,
Yeah.
It's not
You're on the right track, I think.
No,
So
but
that's
it
6 over
cancels,
3
6 over
yeah.
6 is 1.
I
Yeah,
just-
yeah, okay, yeah, you're right.
I think you're still needing to consider the whole, the chain rule factor of times -1, but yeah, you're getting the right idea there.
Oh, because it's a geometric series.
What?
what?
No, I don't see it.
No, I don't get it.
I don't.
Come back around to it, see if you can get to the, see if you can get to the polynomial
Oh,
first.
wait, no, I get it. That's so easy. Why am I so dumb?
Okay.
Yeah,
Wow.
so critical of ourselves.
This is a lot.
No, it's this.
This is a lot to take in, yeah.
Yeah.
There's a lot going on. Lots of little details. So yeah, I think,
So if it's,
with these Taylor polynomials, you just gotta go slow, because like, any one part of them is really easy, right? Like, can you do a derivative? Yes. Can I plug numbers in? Yes. But when you're doing a lot of it all at the same time, I think that's where things will go awry.
that's wacky.
I don't like that that works.
I don't like that that
doesn't-
word.
That doesn't, that shouldn't work. It's not allowed to work.
Just water bottle keeps it nice, keeps the water nice and cold.
We can look at it, Sam, we're gonna look at this graphically here in a moment as well.
That was fun.
Would there have to be a well?
Just write it out with a sigma.
Well, so, yeah, we're gonna look at this here in just a second. The whole graphical thing is a really good thing to look at. And we'll look at that for sure. All right, well, let's do this real quick. So I think the first thing I would do is I would say that this equals 1 minus x to the -1. Starting off, does that make sense? When I'm getting ready to do some derivatives, this will make it easier. Okay, so my polynomial will be this right here. I'm going to write p of x equals, my first term is going to be f of 0, which is just 1, right? Okay, so we start off there. Pretty easy start.
Crushed that part.
Yes. Plus, well, now I need to start finding my derivatives, right, to find these other terms. So I'll just do that down here. So I'll go f prime of x equals -1 minus x to the -2 times -1, right? That times -1 is your chain factor. It's got to be there. So now, when I do this, don't I get basically positive 1 minus 0 to the -2, which is 1. Okay, so there's my next term, 1x. Just write that as x. So you might be thinking that these derivatives are going to be super simple, but they do get a little more complicated. So then my second derivative would be, -2 times 1 minus x to the -3 times -1, which of course is really 2 times 1 minus x to the -3. So when I plug in a 0 there, what do I get? 2. Okay, so this would be plus 2x squared over 2 factorial. And we only have to do one more, but I think we'll see the pattern here pretty quick. F triple prime then would equal negative 6, 1 minus x to the negative fourth times negative 1, which of course is just 6 times 1 minus x to the negative fourth. Plug in the 0, and what do you get? So I get plus 6x cubed over 3 factorial. And this might be where it would be very beneficial for us to do some simplifying. So I would say then you could rewrite as p of x equals 1 plus x plus, well, 2 factorial is 2, so the 2's would cancel. And then 3 factorial is 6, so the 6's would cancel. And so you start to see this really nice pattern develop like this. And you could do a few more terms and maybe confirm to yourself, man, it sure looks like it. Indeed it is, plus dot, 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 plus just x to the n. And that would be the simplest version of this particular Taylor polynomial. Okay, so Jack kind of let the cat out of the bag. Let's talk about this. These questions in the box over here. Do you recognize this function in series pattern? And Jack, you said it was?
Geometric.
Geometric. Okay, so let's talk about what makes a geometric series or a geometric function a geometric function. Geometric is essentially saying you take a numerical base, right, to a variable exponent. And notice, let me see if I can illuminate this a little bit better. If I wrote this, would this be a little more clear? If I just use the letter R, what would the letter R stand for?
Ratio.
Yeah, common ratio. So isn't that what a geometric series is? It's some common ratio raised to a variable exponent. And so in this case, the only thing that doesn't seem to fit very well maybe is the 1. But what's the 1? X to the 0, R to the 0, right? That's just a 1. Yeah, so this actually fits super nicely. For the yellow box up there, what's the common ratio? X. Okay, so if you recognize that the common ratio is X, maybe this over here will make a little more sense. Why would this relationship only be true for that interval?
Because then you
Common ratio has to be what? The absolute value of it has to be between 0 and 1, right? So you could have a negative common ratio. What are all the numbers in between negative 1 and 1? 0 and decimals and fractions, right? So remember that common ratio has to be a fraction in there, like a fraction that's not bigger than 1. And so that's the reason why this works only for this interval, okay? Because X is the common ratio. So the way we would have written it earlier is something like this. We'd have said negative 1 has to be less than R, which has to be less than 1, or we would have written this just from the geometric series test, right, directly. Now there's one more connection that I want you guys to make. I don't know, maybe you already did it. Check out the orange box right here. What does that look like to you now? Say again, Sam?
Oh, is that the 1 minus, or like the sum of it?
Yes. Isn't this geometric series equal to A over 1 minus R?
Oh, that's weird.
Do you see how 1 over 1 minus X is A over 1 minus R, right? Because my common ratio is X. And my first term was 1.
Oh my gosh, Mr.
But that's only if it goes from n equals 0 to
Starting at 0. Exactly right. Does that make sense? Isn't that lovely? So back in pre-calc, when your teacher said, all right, the sum of a geometric series is A over 1 minus R, and you kind of had to just say, all right, cool. I know how to do that. Now you have a little better idea of where that came from and why it actually works, right? Why it actually could be proven to be true. I'd like to show you one more thing but unless you have a question or comment or anything. Okay, so give me 1 second here. So I want to. So here we go. Let's go. F of x equals 1 over 1 minus x. And that's that original function we started off with, right? Okay. So then, somebody earlier, I think Julia said, wait a minute, there's got to be a vertical asymptote there. Of course there is. You're right. So let's say p of x equals, well, so that polynomial we just came up with is easy to type. 1 plus x. What's that? Tangent line. Now we're going to make it a tangent curve, so to speak. Okay. So what I want you to pay particular attention to, in fact, let me do this. Okay, so now you can see all the grid by ones on the x-axis. I want you to pay careful attention to the interval of convergence. So right now, with 3 terms, the interval of convergence is, like right about here to right about there, at least visually, at least where we're zoomed to. And so we'll keep that zoom, and I want you guys to watch this interval of convergence as I slowly add terms. So think about what's happening here. The interval of convergence is getting a little bit bigger, right? But it's very limited by that asymptote on the right, isn't it? It's gonna not know what to do exactly to jump across that. You can see some increase in size on the interval of convergence. So now we're getting out there. On the left side, we're getting closer to -1, aren't we? And on the right side, it's almost like coinciding as it heads up towards that vertical asymptote. But it's definitely not quite there yet. Where am I at? 8. So plus x to the 9th plus x to the 10th. I don't know. We could go on forever, obviously, which I am not going to try to do. So, at this point, it's almost perfectly coinciding to the right side, right? We're clearly heading towards that vertical asymptote at 1. The left side keeps getting closer and closer to -1, and you could wear yourself out. Like if you had like 3 or 4 hours to kill, like at the airport and had your computer, you want to do Desmos, you could sit there and just keep adding, and you could get plus x to the 10 billionth or however many you could get there. But even if you did get up to plus x to the 10 billionth, you would find that the interval of convergence seems to stop right there. It's going to keep getting closer and closer, but you could always zoom in a little bit and say, it's not there yet. You could zoom a little bit more. You could get up to the x to the 10 trillionth or something, and you'd say, well, sure, it's getting a lot closer, but it would never actually get to -1. Okay, it's just naturally how it's going to happen, and it further illustrates that common ratio concept when it comes to the geometric series. And for that matter, the polynomial will never show up over there, the way we have it currently constructed. How could I get it to show up over there? Change the centering point, right? But then, of course, that would mess with the common ratio, and it would change what the common ratio is, because now it would be common ratio -3 or something like that, right? That would change all those numbers. So you could get it to show up over there, but it was centering it at 0. It's not going to show up there. What if I tried to center this at 1? What do you think would happen? It just wouldn't exist.
Yeah, I was like, would nothing happen?
There's nothing there, so nothing. You would get undefined the whole time, right? So yeah, every time you get division by 0. So you can't center a Taylor polynomial at a place where the graph doesn't exist. Okay. So what do you think? Any questions there? Any follow-ups? Okay. So let's talk about this. And this is where we're going to go for the last part of our class, and it's definitely where we will go for next time. So you see the blue graph, and the black graph was our original. So when I talk about this interval of convergence, here's basically what we're talking about. We're talking about x values for which, there's an h in there, the blue graph could equal the black graph. Right? So as we talked about earlier, at the very start of the unit, if the number of terms approaches infinity, then the approximation becomes perfect, right? So, we obviously can't write an infinite number of terms.
Unless.
Some.
Yeah, well, we can't actually write them, right? We can't actually just like write them out. So, that's when we calculate partial sums, right? We say, hey, let's just do the first 10 terms or the fifth degree approximation or whatever we're instructed to do, whatever we want to do. As soon as we stop the polynomial, there's inherently going to be some error, right? In fact, you can see, if I were to do some zooming in, my centering point was 0. You can, see it right there. It looks really good. It's perfect right there. But as soon as I move off of 0, this is what we did yesterday, I start to see some error. And we got enough terms where the error is not very obvious, is it? Let's just do this. Boy, it's tough to see. I'm so curious. When is it going to happen? Have you ever wondered how far Desmos can zoom in?
Yeah.
Let's find out. Keep going, Desmos. You can do it. Let me see if I can just get this right in the middle. That would be lovely. Nope. Can you see any error there yet? Oh man, it's like not wanting to.
Just cut off.
I think it is. It's totally cut off. Yeah. So I put a lot of terms in there. That's why it's
Did a good job.
really good. Yeah, tons of terms. You're going to get a really good approximation. Wonder where we'll first be able to see it. Man, we still are at super tiny numbers. Look at that. Negative 4.2 times 10 negative 7th. Hey, we found out how far Desmos can zoom in. Now we know. Look at that. Let's go out a bit. Why, it's tough to see. How deep does this rabbit hole go? When I talked about just trying to kill time, here you go. Oh, that's interesting. Like, we're up to like fairly large numbers. Like we're up to like 13 thousandths. Does this illustrate how good the approximation can be? This is an unintended illustration, but there you go. Logan and Meg, hope you're enjoying this. Check it out. You can see it's a curve again. Whoa, that is fascinating. No, sorry, I'm like genuinely fascinated by this. There we go. Okay, so right in there, we got to get all the way over there to like negative 0.6 before we start to see error. At least on this. I guess we could do some zooming in now and see it better. Here, we'll go back in. There we go. See, there was error there all along. We just couldn't see it very well. So basically what we're going to be doing is we're going to be bounding our error. So we talked about this before with those alternating series. We said, hey, the error for a partial sum with alternating series is bounded by what? What was that error bound? First neglected term. The next one, right? So a lot of these series, in fact, the e to the x one we just did, and then the geometric one that we just did, neither of those was alternating. So when it comes to, saying, hey, the blue graph approximates the black graph, yet we want to know about how far off we could be, we can't use the alternating series error bound because it's not an alternating series, right? They're all pluses. So we need a different way to do that. And so we are going to now look at what is probably the scariest sounding thing of the year, maybe. And it's called the Lagrange form. Lagrange, yes. Sounds, and it's the scariest looking thing for sure. I'll try to break it down for you so that it's not quite so scary. So
Math of English.
here's basically the plot. The alternating series error bound will only work for alternating series. The Lagrange error bound will work for pretty much all the other series.
Great.
Alternating or otherwise. It'll work for alternating. You'll find that alternating will give you a tighter error bound typically, or sometimes, which is good, right? It'll give you more precise. But this will always be fine. And there was a really long proof of this. In the first couple of years that I taught this class, we did the proof, and it took up like the entire front board. It took an entire class. And as our contact time has gone from this to this to this, things like that have gone out the window. So I was told last year that there was a nice proof of it on Khan Academy. I haven't watched it myself, so I don't know. I can't make a judgment as to whether it's great or not. But if you're really curious, it'll probably take, I don't know, probably like a 30 or 40 minute proof, 25, 30 minutes, something like that on Khan Academy, if you're curious. Anyways, it's up to you. It'll take a little while. There's some interesting stuff in there. It's the type of thing you would see probably it'd be like a beginning analysis question, like in a upper level bachelor or lower level master's degree type of a course. So for whatever that's worth. Okay, so let's start on some stuff that we can maybe agree on because we've seen this before. Would you guys agree with me that this is an expression for error?
Minus p.
Right, remember the way that you find error is you take the
Oh,
actual
okay.
value
Yeah.
and you subtract your approximation, and that's how you find how far off you are. So just from a notational perspective, this would be the actual value. This would be the approximation, and the way that we find the error is to take the actual value minus the approximation. We usually absolute value it because we usually will express error as a positive number. So whether we're above or below, we'll just always absolute value, just find the difference there. Does that make sense? Okay. It's the same expression we use with alternating series as well. Exactly the same. Okay. So Taylor's theorem essentially says that, and this is going to sound a lot like the alternating series, and in some cases it is the same, but in a lot of cases it's not. Taylor's theorem says that the remainder, or aka the error, is equal to this right here. I'll put this in a box. And we'll break down what this is here in a second. I know it looks scary. And it even, later on, you see the word max in there. Like in a math equation, they just wrote M-A-X. I get it. It's a little bit scary looking. So I think what is down here that I'm going to put into a blue box. And check this out. If you wanted to take that thing in the orange box and just try to use some relatively easy to understand language, we would say that the maximum error, or the error is bounded by the maximum value of the n plus 1 term. And you might argue and say, well, wait a minute, isn't the n plus 1 term just the next term? And the answer is sometimes it is, and sometimes it's not. Do you remember, I'll write this off to the side and then I'll erase it. Do you remember how sine, I'll write this up on the top. Remember how sine Maclaurin polynomial is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus ... So in this case, the next term, wouldn't it be x to the 7 over 7 factorial? Whereas the n plus, get this please, the n plus 1th term would be x to the 6 over 6 factorial. So if there's some skipping in the terms, like in this particular case, then the n plus 1 term would be different than the next term. Does that make sense?
Yeah, I mean,
Yes.
N plus 1 would mean the next term if the powers go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
5 plus 1 is 6, not 7.
Correct. But when I say the next term, if I literally am talking about the first neglected term off this alternating series, well, I would say, well, what's the next term? Well, it would be minus x to the 7 over 7 factorial. But if I said, what's the n plus 1th term? Well, what's 5 plus 1? It's not 7.
That's right.
As far as I know,
That's right.
it's 6.
What's the proof?
And so that would be a different set of numbers. It would be a different data point that we would use to bound the error. So because of that, because an alternating series error bound might skip over something, like in this case the 6th degree, That's why the alternating series error bound can be a little more precise. Okay, so I think you guys are going to find in practice this is not that bad, really, honestly. It looks really scary at the start. I get it.
This is not that bad, he says.
I said, wait. I said, in the end, you'll think it's not that bad. At the start, you're going to think it's really difficult. Let me see if I can explain a couple things here. And then, I don't know, well, maybe we'll do one. We'll see. Okay. So let's break this down into what is actually going on. I've done this in the box, but I'll talk about it again. So the error right, is bounded by. So what does that symbol mean?
Less than or equal to.
And then if we translated that into like more regular English, wouldn't we say is at most? The error is at most, so I'm bounding the error. I'm saying it can't possibly be any higher than this. The most it could be is this right here. So the error is bounded by, and here's that Lagrange form of the error bound. Let's talk about what these different pieces are. C. C. You've seen C before, haven't you? Centering point. That's right. Centering point. Okay. So N, and this would be true of all the N's that you see here. Isn't N just the degree that we went to? So I'll put degree of polynomial. So if we went to like the 9th degree, N is 9, therefore N plus 1 would be 10. Okay, so N is just the degree, just like we've done on all the polynomials we've done so far. And that's true of this N as well. It's also true of that N right there. The X is the value. Nope, C is the centering point.
No, yeah, no. I was sorry.
Okay, X is the value that we approximated with. So remember how I said once you move off the centering point, there's going to be error? So like on that last one we did, the centering point was 0. So what if we decided to try to approximate the black function with the blue function at like 1/10? Well, X would be 1/10. It's the number that we're trying to use to approximate. So obviously, think about it like this. Here's something to think about. If the centering point, let's just say for instance, let's say the centering point was 5, and then I tried to approximate my function using my polynomial at 5, wouldn't this right here, in that particular instance, just be 5 minus 5?
Yeah.
And what's the error? 0. So at the centering point, there's no error. But if my centering point was 5, and I thought, well, let's see what happens at 5.1. Well, now my x is 5.1. 5.1 minus 5 isn't 0, so the error wouldn't be 0. You following? Still remember the graph we just looked at? Maybe it would be nice if I split screened this with the graph, but hopefully that makes sense. Now, the last thing that people get really weirded out by is this thing that I'm highlighting in green. It's the N. It's max, what in the world, blah, 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 Z. Okay, so what that means is this. It's the maximum value of the N plus 1th derivative. And how you find this is going to be the trickiest piece of this. It's going to depend totally on the information that you have. Sometimes it's going to be very easy to find analytically. Sometimes you're going to have to do it graphically. Sometimes you're going to, God forbid me say this, sometimes you're going to have to make an educated guess. Really, seriously, honestly, you will. But it'll be a very educated guess. It won't just be like, oh, 20. It'll be educated, for sure. And then Z, and this is mentioned over here in the little box, Z is just some number on the interval between X and C. So if you're going to find the max value of the N plus 1th derivative, it probably should have to do with the interval that we're actually working with. So Z just stands for some number on the interval we care about. So let me put it like this, and this will be where we close today. You know, like when you're in, I hear this all the time in Algebra 1. They've learned not to say it by this point, but have you ever been to that place where you're in a math class and you basically say, oh, just give me a formula where I can just go plug, 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 done. just please give me a formula. You know, it's like at the lowest level of thinking.
Well,
But-
here's your formula.
Can you understand why people would want that?
Yeah.
Just give me a formula and I just go number, and I'm done. This is almost like that. Let me just explain why I would say that. These
Because it's calculus.
These elements right here, I'll highlight for you in purple. These elements are all completely canned. They're formulaic. Like, you're going to know what your X is. Just plug the X in. You're going to know what the C is. Just plug it in. You're going to know what the N is. For goodness sake, just plug it in. The only thing that's going to require any real thought on your part is figuring out that max value of the n plus 1th derivative. And sometimes that's going to take just a little bit of thought. Sometimes it's going to take a lot of thought. But everything else, all the guys, honestly, all the stuff in the green box is a formula. Plug, done. Honestly, that's all it is. The blue box, that's where you're going to have to think a little bit. And that's okay. Really? Looks bluish to me.
That's definitely
It's
purple.
purple.
Yeah, it's purple.
I can see why you'd say a little
It's
purpley.
like the color of Peyton notebook.
Wait, what is purple?
They're saying my blue box is actually a purple box.
That's purple.
It's hard to say. Okay, so when I see you all tomorrow, we're going to be working on, and you're going to get some reinforcement with the whole making a Taylor polynomial as well. But we'll be looking at this Lagrange error bound, and that'll be that.
Why
So.
didn't I just take common stat?
This is gonna be hard to watch.
Come on. Oh, this is so much easier.
This is so much more fun.
So much more, yeah. I
I would rather.
have a good rest of your day, you
It's
guys.
gonna be fun learning over.